Okay, so I will present my research in optical measurement for basically using tapered fiber coupled with PMMA microresonators for specific applications as wavelength sensors. So a little bit about the fundamental principles. I guess Christians and Lasse already did some some things, but ideally we have resonator which is coupled to and if the coupled light source is basically continuous, will interact the light that's going into the micro resonator. And if we watch from the resonator, from, let's say, using camera or some sort of detector, we will see a spectrum. And if we watch the light source or the coupled light source detector, we will see the transmission spectrum. And also, in the micro resonator, we have different modes, like the main mode, which usually people use for normal sensor applications, and then there are more higher level modes. So my work focuses on industrial available PMMA whispering gallery mode microresonators, which the producer is Banks Laboratories. And on the picture in the right, you can see how they look under the microscope. Obviously, one thing that is with polymer or these PMMA microresonators is that the surface of them is have a lot of impurities inside them. And plus, as I said before, in the microresonator, there are these higher level modes that usually interact with either surface impurities and things like that. So we have a specific experimental setup where we have the tapered fiber, to which the waste region we attach the microresonator, and then watch with camera the intensity changes based on like either temperature or wavelength differences. So this is how it looks under the microscope. The first picture is the microresonator coupled to the waste region without any light, so basically laser light circling inside the microresonator. And the last one is the picture how it looks in the dark when obviously the light is circulating inside the microresonator. And what we can do is basically split the microresonator into specific regions. In this picture, we have 4 regions. And as we can see, for specific wavelengths, in this case wavelengths, the intensity in these regions changes. And that is due to the fact that there are these multiple modes that are reacting with multiple surface impurities of the microresonator. So basically, what my research focuses on, and basically my group's research focuses on, is the usage of basically 2 negatives, and we turn them into a positive, which is multiple modes and surface impurities. So as it turns out, we can use them in our advantage. So, and this is the intensity changes. As we can see, we can monitor the intensity on each the specific region if we write a program that uses image analysis. And for each region, the intensity changes quite drastically, and it's quite hard to actually, it's almost impossible to get 2 specific regions with the same intensity. And what we can do is make intensity maps, and based on these maps, we can create a working wave sensor that's suitable for telecommunication application, or and also this could be integrated either temperature sensor, humidity sensor, or for specific type of sensing applications. And yeah, also we have done few COMSOL simulations where we have added surface irregularities and then watched in what kind of intensity light escapes from, for example, two different regions. Then here's like a bit better picture. So if we have a perfect resonator, then the light stays inside the resonator, and obviously nothing can escape. But if we have some sort of impurities, like the surface deformations, then some light can escape. And if we have some particles that are attached to these surface impurities, almost light can escape. And that's obviously what we are observing in yeah, and based on these simulations, we can actually validate the results of our experiments. So yeah, thank you for your time. Does anyone have some questions?
So we don't see questions. Let's thank all our speakers for the presentations.